thank you very much, Peter, and everybody else who's organizing, for the invitation and for the opportunity to share a bit of my very abstruse and unknown work. So you may have noticed already, I've already changed the title, so I've moved it to Lie algebras and higher gauge theory, because I also had the impression that there were more physicists maybe than mathematicians, and also my own point of view is heavily physics biased. So I want to describe Lie algebras in some detail, but my main interest is how to apply this to higher gauge theory, why we need it. So the first day will be like our first hour now will be trying to see why is it necessary, do we need it at all, and how can we use how these structures, let's say, can be justified from a categorical point of view to be useful for a certain, like physics, for certain types of gauge theories in physics. It was friction was working well for a bit, right? But it's one of those things that just accumulates.
I need to press a little bit.
How did I?
Books or
something? Well, because my tablet is between this and this, so just maybe we could put this somewhere else. I guess we could put it. The idea with the chair. Yeah, if they move that here, we could put it on the chair. Oh, yeah, that's clever.
That's actually much more.
Yeah, that's oh, here. Excellent. Okay. Well, that should work. That's what. It's strong enough. Yeah.
Okay. From now on, you have to come to all of the events.
So we're going to have a little quick review of what gauge theory is, how it works, and so on. For those who are not physicists and who are not overly familiar, we're going to see a little bit about category theory, normal one-category theory, and functors, and we're going to try to see how we can look at gauge theory in that language, because as it is a very general kind of structure in which to put mathematical objects, it's as is often the case, it is also much easier to then generalize to situations we haven't yet considered, and actually might hold more information than the language we usually use. And then on part two, in this part one, I'll also show you what the problem is with trying to do gauge theory for higher P forms. So imagine, for example, Young-Mills or super Young-Mills theory, which is just Young-Mills, or even electrodynamics, where instead of having an F that is a 2 form, you want, just for fun, to have an F that is a P form. Could you write Young-Mills theory for that? And it turns out you cannot unless the structure group you're interested in is abelian. And of course, nature's internal symmetries are very rarely abelian, so that's not good enough. And especially if you're going to be dealing with extended objects, not point-like particles, I'm going to try to convince you that somehow this problem has to be solved in some other way. And in part two today, I'm going to show you how this simple idea of a category can be lifted one step up higher to a 2 category, and therefore 2 functors, and in principle can be lifted to 3 categories and k categories if you want, but we're going to look in detail at the example of 2 because it's the easiest and it's the best studied as well. And I'm going to show you how that the problems presented in the first hour can be solved. And hopefully have time to quickly introduce the absolute generalization to n dimensions, to any n bigger than 2 as well. So, and I'm going to try to do this while writing, which I hope, I think I should be able to do. So, yeah, and then for the lectures 3 and 4, this is the list of the things I'm discussing, but we'll get to that in detail when the time comes. So, gauge theory. Oops. Let's see, page. Can you read up here? Too small? No, I cannot. So, okay, hang on. Sorry. Where does it start? Here? Yeah, okay. Gauge theory. So, most of you know it's basically the fundamental thing in theoretical physics, right? We have some sort of a theory, physical theory defined on a principal bundle that is a fiber bundle with some, I can't get rid of that dirt up there, right? Can I? Great, let's just ignore it for now, and hopefully the next slide will be better. So we start, let's say, with some sort of space-time manifold n, exaggerated n, and we put a structure group G. I always draw it a bit like that to visualize that at every point in M there will be endowed with this G fiber. And then if we have particles, point particles that move along world lines on this space-time manifold, so let's say from x1 to x2, then these particles will be basically described mathematically by sections of this principal bundle. So phi x will be sections of the bundle. So they will be valued in some representation of G, and they depend, of course, locally on x, on where they're at. And we know that we can relate a phi at some, if phi from some x wants to be related somehow to some phi prime at some x prime. So the phi has a prime here because not only does it matter where you are on x, but it also matters, we want for gauge theory the internal structure group to act locally. So we want there to be a possible, a charge under this gauge group for the field to be different at every point without any, some restriction, as we'll see now. But basically we want there to be, different charges at different, we want the possibility of different charges at different points. So how do we usually write this? How do we relate this phi prime x prime to an old phi? Well, the usual way is, don't worry about this symbol, but the obvious way to do this is via this thing here is a group element of G, because A, I will take it to be in the Lie algebra of G. And the gamma is this little path from x1 to x2, and you can see how the gauge connection, which in this case is also one form, is traditional gauge theory, practically generates little changes locally at each x that will happen to the field in the sense of within the group G, so as it lives in the representation of G. And we integrate these little infinitesimal changes along the whole path, and we end up with a finite change to phi, right? And this p here is crucial because once we expand this exponential, like what will be this thing, what will this look like? It will be 1 minus q integral over a. Q is obviously the charge under of that field under G, right? Or the group parameter if you want. And then we will end up with things like integral of A over gamma, each of them, etc. But in here, the A's will be, the A's are one form, so they can be written like this. Or in terms of the parameter that parameterizes this path gamma, you can write it. This is all very, very boring maybe, but it's worth reminding ourselves for what will follow. So each of these will be depend on the tau parameter of their path, but these are two different integrals over gamma. So one of them will be taken at, we will end up with products like a at tau and a at tau prime integrated over both d tau and d tau prime. And okay, so we could just write it down like this, but at the moment that a at tau and a at tau prime do not commute, it's not obvious in which order you should put them in this expansion, right? If this is non-zero, meaning that G is non-abelian, right? Then we have to start making some choice. At the end of the slide already, okay. So we have to start making some choices about how to order the connection fields in that expansion, right? And the usual way to do it here, it's very easy. I mean, it's a very easy choice to make. We have one path, one parameter, so we just say we will path order them. So this is path ordering, meaning referring sorry, this is very, well, I have I have an updated version of the notes that that I sent to Peter, where this stuff is written out in a cleaner way, so you can confront those and just listen for now, even if the writing is off. But anyway, this path ordering just means that we will choose to order them in such a way that the things that depend the things at the smaller time, or at the smaller tau, sorry, are always set to the left of the things at the higher tau, just like we do in perturbative quantum field theory, when we time order products and so on. You know how to do it. You put in some thetas and you can do that. So that's not here. It's no problem. It's an obvious choice, and that P just indicates that this choice has to be made. And then we will end. And then okay, this is basically our rule for how fields finitely transform along this path. And very nice. Now we've introduced this A, and if you remember gauge theory, this A is basically, you remember what a connection does in terms of when you're looking at a field theory and you're writing derivatives in dynamic terms for the fields, you have these d mu of phi that end up, so you have these d mu's that go into a d mu, which will be equal to d mu corrected by this connection 1 form, some factor, and so on. And basically the fact that we can then have let's say local symmetry transformations, that is gauge transformations, that change the charge of something at a point under that gauge group, and phi as well as A change under this transformation, and A changes just in the right way so as to compensate the change in phi. And we now have, this is called a covariant derivative because it's covariant under this group G, and it makes sure that an action that we write in an invariant way, so we will have things of the type d mu phi is guaranteed to be overall gauge invariant. But okay, that's not so important now, but I mean, we all know that, that's all obvious. But okay, so once we have this A in our theory, that's a new field, and that can also have physics. So you can then put into your action, you can add things of the type f squared, which is basically f mu nu, where f is equal to dA, and if it's non-abelian, if the gauge rule is non-abelian, we can have an A wedge A, and we have an A wedge A in the curvature as well, or with the wedge I mean antisymmetric product, so there would be a commutator there if you want, whichever way you like to write it. Anyway, we now have this f, and so we can add terms to the field theory for the physics of the A itself. And okay, that's what we know, and we do, and we do Yang-Mills theory for, I don't know, for instance, SU3 if you want, non-abelian, and you can do it. You can write it down. It all makes sense. It's all invariant under everything we want it to be invariant under, right? So you might have the obvious question, say, okay, why not consider higher p-form connections? Why does A? Let's see. Oh, I wonder.
Maybe you should disconnect and reconnect.
Yeah. Okay. It's getting worse, isn't it? Okay. So disconnect.
No, not from the Wi-Fi.
Sorry.
AirPlay.
Oh, okay.
Where is that?
The screen share, you mean? Yeah. Maybe the full screen isn't such a good idea. I think that's good. Maybe if I do it like this, right here. Okay. Well, we'll see how it goes. Anyway, so you could say why only one form connections A. You might be curious, can I do something like or Yang-Mills theory, let's say, for P forms? Why not put H squared into an action where H could be any kind of a P form. So factor U1 to UP, dx U1, dx UP. Now you could say, why ask something that you don't need to ask? You might be happy with just paths, point particles moving along paths, and really, why, as a physicist, why do you care about connections? Only to know how to change your fields along these paths. But nowadays, many quantum gravitists from various schools of thought, let's say, are pretty convinced that at high enough energies or at small enough distances, the concept of a point and of localizability at a point is kind of is not. I mean, it's quantumly not accurate. Let's say, unlikely to be accurate. And then one wonders, does it make sense to even talk about point particles anymore? If we don't, if the point itself kind of loses meaning. If we're looking for a quantum theory, of course, I mean, classically, who cares? But if we look at it close enough to be aware of the quantum effects, then, okay, string theorists answer this question by saying, okay, we'll look at extended objects. We'll start with strings rather than points, for instance. So, for example, you would have then, if you consider the string to be your fundamental particle, you have your little string parameterized by sigma, which moves through time, right? And as it moves through time, rather than describe a world line, obviously describes a world surface, right? So at that point, it becomes clear that somehow, if we want to somehow find an infinitesimal generator of transformation, if this whole thing is also endowed with some sort of a structure group G, which of course we need some internal symmetries. We know that our particles are somehow even defined by them, right? So once we have this group structure, we want to know how a field, which now depends on an x that depends on both sigma and tau, how this field changes along the surface. A one form will maybe, what's a one form going to do? It's going to tell us in each of these points how to move in only one direction, right? If we want to span this little surface, we have to already start thinking about maybe two forms you could intuitively imagine, so that, a little, I write it as if it was a two vector, but that it could basically move you along the surface, along little blocks of little squares of surface, and tell you how to move this to, let's say, phi prime at some x prime, right? And so intuitively you would say, okay, I could look for something of the type, I would call this world surface sigma, and I could integrate some sort of a B, where B still lives in the Lie algebra of G, but B is now also a two form in this case. And of course, if we were looking at even bigger objects like brains and so on, we would be talking about 3 forms, 4 forms accordingly, to somehow be integrated along this surface to give us some sort of finite transformation for a phi that goes from here to a phi that lives up here. And what's the problem here? Again, we'll have to, at some point, decide about some sort of an ordering here, right? We have to decide how, once we expand this exponential, how to put the B fields with respect to each other. A B at a specific sigma and a specific tau. So let's say here we are at tau 0, here we can be at tau 1, etc. Here we can be at tau 2, So once we have products of the type B of sigma and tau times B, sigma prime, tau prime, we have to decide who goes first and who goes second. So you say, okay, earlier we just ordered along the time, right? Along the path tau, or the path parameter tau. We could do the same now. Well, and just ignore sigma and just go along tau constant surfaces, right? So, yeah, basically just order along tau. But that's a problem, because in physics we also want somehow some sort of space-time symmetries to apply also, and we want specifically this kind of worldsheet to be reparametrization. I mean, under reparameterizations of this worldsheet, we don't want our physics to change. And smooth reparameterization of this worldsheet, they can mix around sigma and tau, right? So whatever was a tau constant surface before one of these transformations, not a tau constant surface, tau constant line, let's say, anymore after. So if we decide to order along tau, we've already broken the reparameterization invariance. Can we find some very specific combination of sigma and tau along which to go? Well, maybe we could for one case, but what reparameterization is not going to mess that up? And you want any reparameterization to leave the physics here invariant. So that just seems to be like a no-go. And of course, again, I mean, it's fine as long as if G is abelian, if G is abelian, putting B, let's say tau, or B tau prime is the same as putting B at tau prime, so it doesn't matter. So you can, at that point, you can order along whatever you want. Everything is okay in this case. But if it's not abelian, then it's okay. But if not, what are you going to do? Another way of looking at this, which is very ad hoc now, because I'm basically showing you the problem in such a way that I will solve it later with the solution I already have. But I think it's still a way to look at the issue. If you're not convinced by the reparameterization problem, I'm going to draw a big picture here of the same Warren sheet, and I'm going to say divide this up into little squares. Imagine them to be, infinitesimal as you like. And I would like to know if there was, so if A integrated along the path gamma gave us, A integrated along here gave us a group element in G that told us about the change of the fields from here to here. Now I imagine that a B could generate, B could generate an element off and on again. Hello? Well, it seems okay, off and on again. I don't know. Well, we'll see. So B could generate another element G in G always, which relates, and this is very sloppily said, but we could say it relates the phi, if we call this little bit of path from here to here gamma 1, and this little bit of path here gamma 2, it could relate phi at gamma 2 to phi at gamma 1. Now, of course, phi at gamma 2, I mean phi all over that little bit of interval. It's not a very precise thing to say, but I just want to, it's just to show you heuristically what the problem really looks like here. So here I would have a B that basically covers this little surface. Here I would have another one, here I would have another one, and here as well. Actually, let me delete that. I will put the G's in there directly. So I could say there's a G1 associated to this little box. Here we go to gamma 3, and we have, let's say in here we have a G2 that covers this little box. Here we have a G3 and a G4. Is this too small? Is it too small? No. Okay. So we have a G3 and a G4, and they take us from, let's say, gamma 1, 2, 3, gamma 4, gamma 5, gamma 6. And you can see in words it's easy to, I've written down a kind of a sloppy, well, an ugly way of writing this. In words it's much easier to say. You can imagine that I could take this bit of path here up to this bit of path here. I could either take this whole path up, let's say I could go from here to here with G3, G1 together, moving this bit of path up to this one, and then again, act again with, so take it up again, and I would end up having to write G4, G2 after G3, G1. and here I'm just basically taking the whole chunk up and up again, or I can split the path into 2 bits and first take up this one, then take it up again, in the meantime leaving the other one down here, and then take this one up and this one up. And in this case, how would I be acting? Well, I would act with this after this, right? And that was G2 after G1, and on that I would add this one, which would be G4 after G3, right? Does that somehow make sense? I mean, if there were group elements associated to each of these little bits of surface, then they could act in both these ways. So either take everything up vertically, zack, zack, or take up one bit first and then compose with taking up the other bit. I mean, which choice I make shouldn't influence physics, right? I cannot have the fields up here, their charge under G, depending on which of these 2 ways I chose to go up there, right? That would be ridiculous, because then I would have infinitely many theories for each surface. I need to decide on one. That's exactly what we want to do with the ordering, right? But then you see that for these are the 2 operations that we have. So for these 2 to be the same, we would need this and this to be interchangeable, right? I mean, we would need at least, for these 2 to be the same, we would need G3, G2 to be equal to G2, G3 for any G's, because I can do this on any bit of the surface, and I can, this is an overall problem. So that would mean that if this is true for all the G's in G, Gi's in G, then G would have to be abelian for this kind of transport to be well defined, right? And okay, you could say, hang on, you've been like extremely specific here. You chose the same gauge group that you had for the paths, and you're using it here. Maybe we should just use one gauge group for the paths and maybe another one for the surfaces. And you can play this game again more carefully. I mean, I haven't been very careful here in how to combine paths, because I've just written this thing here with the gamma. But of course, what's hidden in here is that I have the information of phi at the beginning of that path and of phi at the end of that path, because I know how to relate them via A, right? So in some sense, I am using, for all this discussion to work, I am using information from both A and B. And I have so far assumed that they were both in G, but even if you do this whole analysis much more in detail, looking really at how you have to compose the paths with the surfaces and so on, and allow B to be in another group, you would still end up with actually both B and H having to be abelian. So you're not gaining. I mean, it's a fair guess, but it doesn't really help. So anyway, so that's basically the issue. Is that more or less convincing? Yeah. Okay. I mean, the easiest way for a physicist to look at it is to try to write Yang-Mills theory and just see that. Just sit down, try to make a gauge and reparameterization and variant for the space-time, and you will realize there's no way you can do it unless everything commutes. So, but this picture is going to be useful for how we solve the problem later on. So that's why I wanted to draw it at least once. So okay, so far so good. So little parenthesis now on mathematics, and in particular on category theory, just for fun. Forget everything I said until now for a moment, and let's see what a category really is. So what is a category? It is a collection of objects, which I will always denote with a dot, and here in general I will call them A, B, C, and whatever. And it also has a set of morphisms, a collection of morphisms between any pair of objects, A and B, and I would generally denote them with an F, and I draw them as maps. They are maps between objects, between all pairs of objects. I will denote them with an F, and we usually draw them as like this, as arrows going from right to left, from one object to the other. The right from left convention is apparently makes many of these drawings, when you have complicated drawings, more easy. So I just stick to the common notation. And we have some requirements of these things. So the morphisms, there has to be, oh, let's say, sorry. There, has to exist an identity morphism at each object. So that would be drawn as, you know, a map from A to A, and we will denote that as a 1 with a little a index, meaning it's the identity at that A. We'll see when we see examples of categories that it matters that it's at a point, because categories can be such general objects that God knows what morphisms are going to be. So it's going to be very, very object dependent. This thing. This thing has to satisfy. This identity has to satisfy. Well, first, actually, before we go to that, the morphisms have to be composable. Morphisms have to be composable, and the composition I will write as a dot. So, for example, we could have an F that goes from A to B, a G that goes from B to C, and then we would have an F dot, sorry, actually we would have a G dot F, which maps from A to C, and in diagrammatic form that is easily drawn. We have an A, we have a B, and a C. These are three objects. There exists a map from A to B, which is called F. There is another one from B to C, which is called G, and this has to be equal to some new map in the same category, G dot F, going from A to C. I didn't mention here, these F's have a source and a target, source and target maps, source S and target T. So in this example, we would have the S, the source of F would be A, and the target of F would be B. Just exactly as the word suggests, source and target just tell you where it starts and where it ends. So the source and target of the composition is, of course, now the source is the source of the first operation, and the target is the target of the last operation. So they have to be composable, but not only, this composition has to be associative. Composition has to be associative. The next slide. Easy to draw, easy to imagine. We have A, B, C, D. Oops, D. We have three maps. Let's call them F1, F2, F3, and this, of course, has to be equal to both F1 combined with F2 already after F3. But also to, let's see, the last one was F1, and this one will be F2 after F3, and this was A, C, D now. Notice the letters below, but this is quite obvious. I'm basically saying, if I just change color for a moment, I'm saying that doing this and then this has to be the same as doing this and then this. Associativity. And actually, I've already said it all. There's not, I mean, there is, of course, we can say the identity at each object, or let's say identities, have to be compatible with this composition, or, you know, with composition. So that basically just means that if I have, for instance, some f that goes from A to B, and I have an identity at B here, that this is just equal to just taking f, right? I mean, composing, that means that 1 at B with f is equal to f, just like it's equal to f composed with 1 at A, right? That makes sense. So, I mean, makes sense because these are the usual few basic definitions of, indeed, almost any mathematical object we see in our undergrad days, or any time after that, actually. I mean, it's really the minimum you can ask, some sort of identity, some sort of composability. The associativity is not so minimal, but since we're asking for nothing else, you could say associativity is pretty intuitive. Well, not always, but it's not a huge requirement, right? It's not very restrictive. So you can imagine that a lot of things fall into this idea, into this structure. So for instance, I'm going to go to a new slide again. I have some examples just to make this a little bit less arrowy. So you could take a smooth manifold, for instance, a smooth manifold that I call M. Now, you could say the points on that, points P in M, could be associated to objects of some category. I mean, we'll see if it's possible, right? So the points could be the objects, and the paths gamma between points could be, why not, the morphisms. They do map from one object to the other, and if it's a smooth manifold, there is a path between any pair of objects. So far so good. The good thing is they are obviously composable. I forgot keyword, smooth paths from between points. So they are composable. I mean, you can imagine. I don't think I have to write it down, but you know how to compose two paths. Now I want them to compose them into another smooth path, right? I want whatever comes out to still be in the category if these are going to be morphisms. So I'm going to have to restrict these paths a little bit. So I'm going to say if they are called, this is just a term, lazy, meaning they are constant near their source and target. So if we do a little drawing, we have a path between x1 and x2. Obviously its source is x1, right? Its target is x2. And we have, if we say paths are morphisms, we also obviously have an identity path at each x, which is just the, here called ix2, but here it's always going to be the constant path at that point. And basically to be able to compose two paths into another smooth path, I need them here to be composable without any cusps or discontinuities of any type. So I restrict to the ones that are, I choose those paths that are lazy near their endpoints, let's say. Furthermore, I also need these guys to be, the composition of these guys, of this path, has to be associative, right? Now, that's not a given. I might be, if I take three paths and I combine them, and I take the path that is the combination of these two, or let's say these two, the compositions might be related to the original two by some homotopy transformations, for instance. So it's not necessarily, they're not necessarily strictly associative as is. So I will restrict also the path to equivalence classes, and in particular, that means that we need to take paths in equivalence classes, and I will take these classes to be those of, in particular, I will take thinly homotopic paths. I will tell you in a minute what that is. Take thinly homotopy paths. So a homotopy transformation between two paths, you all remember, it's a smooth way to map from path 1 between two objects to path 2 between two objects. So it basically spans this surface between these two paths if we're in a smooth manifold. And okay, not all homotopic. Oops. Yeah, I take the thinly. So I want to not distinguish between homotopic paths that give me the same finite transformation on a field that would live over this on this manifold. That would. So if I had a imagine I was already doing gauge theory on top of this spacetime on top of this M here, and I was already considering sections on here that have, you know, fields basically that live on top of this thing. Now, you know, in physics I don't need if two homotopic paths give me the same ultimate finite transformation on phi after it has moved along them, then I don't need to distinguish them. However, there are homotopic paths that do not give me the same finite transformation of that field, right? So I want to restrict to the thinly homotopic ones, meaning only the ones that give us different final transformations. And that means if there is this, you know, homotopy, let's say this is from the two paths, gamma gamma prime, this thing here in the middle, I will call this homotopy, I will call it sigma. If I have this so in such a way that sigma at 0 t is equal to gamma, and sigma at 1 t is equal to gamma prime, the thinly homotopic ones are the ones such that the d of this sigma has rank smaller than 2 at each x, at each point in between. So it's basically just, I mean, in physics terms, it's basically I distinguish those paths that give me different group transformations on the fields, or you know, different, yeah, that are actually distinguishable for me physically, and all those paths that are related by thin homotopies, I put them into one class and I just take the representative. So for instance, I don't know, an example could be the path gamma composed with the path gamma minus the inverse path. This is thinly homotopic to the constant path. I go from x1 to x2. It's thinly homotopic to the constant path at x1, right? So once I have the constant path at x1, I don't need to consider all those gamma composed with gamma minus 1 anymore. They're all in that class. And similarly, you know, if you can find a homotopy sigma whose D spans a 0 volume, then they go into the same class. But anyway, this is not so important. It's important from a physics point of view. But from now on, we'll just continue referring to them just as paths. I'm not going to say thinly homotopic, lazy paths, but that's what I mean. So anyway, so far, so we have satisfied everything. We have objects, we have a composition, we have identities, and we have this composition is, thanks to all these restrictions, also associative. So that's a category for one. So taking a manifold with these thinly homotopic classes is one example of a category. There is another example, e.g. 2, which is take just a group, Lie group G, and call that the only object in your category. So you have only this one fat G object. What could morphisms be? What maps you from the object to the object? There's only, well, the obvious choice is elements, group elements in G are the morphisms. Or can they be the morphisms? Do they behave properly? Well, yeah, because they are of course composable by just the group product of G. You know, this is the G group product. This is associative because it's a Lie group. It's associative by construction here. So that's okay. So we have morphisms. They are composable. They have an associative composition, and of course we have an identity, which is just the identity of G, which I will usually refer to as a 1 with this big bullet to indicate we're talking about a category with just the one object. So just like this Lie group can be made into a category of its own, if you have a category of just one object, it also defines your group, because whatever that object is, if there are morphisms that are composable and associative, then voila, we have well, there's one thing missing, and it's invertibility of these morphisms. And it so happens that in this case, of course, we have, of course, all these G group elements in G are invertible, so there exists a G minus 1 for each G, and that is why this kind of category is called, let's say these categories are called groupoids. And in fact, notice that the previous example we had, the paths also all have an inverse path, right? I mean, you can always just go back. If you go up along tau from 0 to 1, you can also go back. So the path is same for n with its paths, which is in fact called the path 1 groupoid as well, because it allows these inverses. That's not a given. So in the definition of a category on its own, the invertibility of these operations is not a request. So it's an extra. So here we have, well, basically here we have, not by coincidence, these two examples of categories, and not by coincidence we'll see in the following. Yeah.
So any category in which you have inverses for the morphisms is a groupoid?
It's called a groupoid. I think that's the definition of groupoid. Okay. In that language, in the categorical language. Yeah. Yeah. Same goes when you go up. If you go to the higher categories and you have 2 morphisms, 3 morphisms, they are also, if everything is invertible, then you have a groupoid. But then they all have to be invertible, not just the one morphism. But yeah. So anyway, so far so good. So already we see that these two examples I made, just random examples, already have a lot in common. So they already have this extra property in common, right? So you can see where I'm going with this, probably. So once we have defined this new structure, this new concept of a category, of course, what does a mathematician do? As soon as he defines something new, he defines himself ways to go, from one of these structures to another, right? So what we need now is functors, which are maps between categories. And what do they have to do? Well, they have to map objects to objects. So let's say I map between category C1 functor to C2. So I will have to map objects to objects. So for instance, an object A in category 1 will get mapped with F to an object F of A in category 2. And they also have to map morphisms to morphisms. So if I have in category 1 some F that goes from A to B, this F will have to get mapped to an F of F, and I use the same symbol, big F, to whether I'm talking about objects or morphisms, because it's very clear which one we're talking about, right? It's not these are not things you can confuse with each other. And you notice that if the source and target of F were A and B,
shouldn't that be FB, FA?
Sorry. Yeah, sorry? Yeah, of course. Yeah. So that's what I was going to say. If the source and target of F are A and B, then the source and target of F of F have to be, F of A, and then the target of F has to be whatever B mapped to. Okay? So far so good. And of course, remember our morphisms had something more. They had to be composable and be associative under composition. So this F has to also preserve the product. Let's see if this works. Has to preserve composition. Again, this is just the usual requirements we have of practically any map from anything to anything. So we want f of small f after g to be equal to f of g, where of course this product is within C1 and this product is in C2. These compositions, right? So if this structure is preserved, then everything is fine, and basically this of course important as well, kind of follows from the rest though, follows from what we have already said, but it preserves the identities. So f of the identity at some A has to be equal to the identity in category 2 at f of A. Right? No, obviously. I mean, without these requirements, we have nothing, right? So this is, again, it's the minimal set of requirements that make somehow sense. And okay, so what? So what is that these two categories that we've looked at, the two examples we've looked at, they were actually, I mean, for us, normally quite different objects, right? One is a group structure. It's a group is a very specific thing. The other one is a manifold with some classes of paths and so on, that these things would be considered the same thing in some languages, maybe not obvious a priori. But what's even less obvious is that you can construct a functor, a map between these two, relating all these things to each other. And so far, yeah, okay, I can map things over. But actually this condition here gives you, I mean, it is a condition, right? So it does give you information about how the things from the one side have to interact with the things of the other. Well, I'm going to say it like that, and I'm going to show you what I mean. So the question is, does there exist, I'm going to write it like this, a functor from the path 1 groupoid, this is the path 1 groupoid that we saw before, and G? That is the question. And well, yeah, there is. I mean, I went on and on about it at the beginning, telling you all this obvious stuff you already knew. But in fact, okay, first of all, let's go step by step. The objects in the path groupoid were the points, right? So the points, let's say xi, have to get mapped to, well, the only object in G is G, right? So every point gets mapped to G, right? What does that mean? Well, my nice little drawing of all these space-time points with their G fibers at every point was saying exactly that, right? That I have a way that I basically associate to every point X a group G, and of course there is the projection map down here, but this is definitely surjective because I'm mapping every point X to, every point X is getting a G. And so far, good. Now the morphisms in the path groupoid, they were paths, right? Paths gamma. And they now have to map, if this functor exists, they have to map to group elements in G, right? So a path between, x1 and x2, and I mean it's really painfully obvious where I'm going with this, has to map to some sort of, let's say, G, some group element in G, right? By definition of functor. Well, and it has to preserve the identity, right? So the identity is the constant path has to go to the identity of G. Okay. Well, anyone want to guess what this map could be? Feel free to shout it out. But I suggest taking a path gamma to something like that. Does it make sense? I'm taking a morphism from the one side to a morphism on the other side. This thing, now we haven't yet established does it satisfy everything, but so far it's looking good. the identity is looking good, right? The constant path will just give me an e to the 0 here, roughly speaking, so I'll just get the identity on this side. For composing paths, now we have to, well, I mean, why not? Let's write it down. If I take the composition of gamma 1, gamma 2, according to the rules of functors, that has to go to, well, yeah, by this definition here, it'll be gamma 1, gamma 2, okay, right? And because the product structure has to be preserved, remember the last rule, sorry, the second last rule, this one, oops, this one here. What does that mean for us down here? Well, it means that this has to be equal to P E minus Q gamma 1 P E minus Q gamma 2, right? And lo and behold, we have kind of defined ourselves a connection, right? We have said how a connection has to behave under composition of these paths and so on. We know how it's supposed to behave, how, you know, we know its identity, we know basically everything we need to know about this one form. Of course, here, for this to be a group element, you know, it goes without saying that A has to be in the algebra of G. And it is a one form, it has to be a one form because I'm integrating it along a path anyway. And I mean, you know, everything is fixed by this map. I mean, we have everything we need now. And okay, you might say, well, yeah, I have restated the obvious. But if you hadn't known anything about gauge theory before this, and you had just said, look, categories exist, these are examples, and you had somehow magically come up with this functor, you would now already know a lot about at least about the connection one form that allows you to do gauge theory, right? And we were saying, you know, until now, that we had big problems doing gauge theory for extended objects, so maybe, since there we are in the position that we know nothing about the physics, let's take this approach, this point of view, and see if it leads us via this looks, you know, this looks like a convoluted way of doing gauge theory, but it might, in a situation where we know nothing, it might be the answer, right? Might be the way to think about higher gauge theory. Or at least, we could at least worry about this whole higher holonomy problem. Higher, and by higher gauge theory, I always mean just with involving higher form connections, right? And I think, what more did I want to say? What time? How much time? Where's my time guy? It's gone. Has anyone kept track?
I think we're close to 1 hour.
Close to an hour? Okay, that's fine. I think. Well, I could give you a little bit, just 2 minute, like 2 minute motivation maybe of why these extended objects, why these extended keyforms and so on. There is, of course, you could say, in some sense, strings don't yet preclude the dealing with point-like objects, right? Because anything we really do with string theory effectively when we're trying to get towards physics is we're talking about string endpoints ending on branes, right? So that's I mean, I don't know, I guess there's not that many string theorists here, but maybe this is something that just folkloristically everybody has heard about, or maybe that's optimistic, I don't know. But let's say we take a stack of dp branes, p meaning the dimension of these branes, and we have one of these wonderful facts of string theory is that when we have open string endpoints ending on a stack of dp branes, and then in time describing their own little warn lines on these hypersurfaces, then the effective theory here of this endpoint, is Super-Yang-Mills theory in I guess p dimensions. So basically, you know, with some UN gauge group, where n is the number of brains that I have here. So if it's only one brain, I have a U1 theory, very nice, nothing's happening. But as soon as I have stacks of brains, then I end up with these non-abelian groups. And okay, I'm not going to get into this, but the point is that what I want to say is that in M theory, we don't have one dimension. So you could say, okay, we're still even within string theory, let's say that anything real, anything physical is always happening on these hypersurfaces. So I'm really only interested in these points anyway, even if I start with extended objects. But if we go up one step to M theory, for instance, that's not this kind of scenario doesn't exist anymore, because in M theory we only have M2 brains, so that means 2 space dimensions moving through time, and M5 brains, so they have 5-dimensional. So at best case scenario is that we're going to have stacks of either M2 or M5, doesn't matter. But the best thing we can have here is a 2-brain ending on another stack, and therefore already describing a Warren surface. So your smallest dimensional thing here, even if you're only interested in effective theories and in physics and something that could eventually one day maybe give us a standard model or whatever, even then you're going to have to deal with these one-dimensional objects. Yeah, that's it. I'm just saying, I mean, this is, let's say, coming from that world, this is my main motivation. I still think, you know, just the fact that even in other quantum gravities, the point doesn't make sense is motivation enough to start thinking about extended things in any case. But for a string M theorist, it's definitely a necessity. I mean, sooner or later, and in fact, all the approaches to, you know, effective theories on stacks of M brains and intersecting brains so far have failed at some step, on some requirement, and not least because this is basically something we can't properly write down.
But even though intuitively one would expect that there you should have a two-form gauge field, we know that for M2 brains actually the low energy physics is described by a local quantum field theory, the ABJM field theory. I don't know.
Up to a point, right? I mean, it's still. Well, actually, it's a good question. I don't remember exactly how successful the ABJM. I mean, does it really? Well, actually, I will show you one thing in the next lecture where the ABJM models and also the BLG models that were proposed before, ultimately the structure they present is actually a 2-gauge group structure. It's just written in a weird way. So I will show you that they are actually, in some sense, a higher gauge theory, but a very strict one, so that it can be easily confused or easily, I mean, it can always be written in terms of normal Lie algebras and relationships between them. So it'll look a bit convoluted, but it's still, the ingredients are still Lie algebras and you know. But if you look at them in my language, that's already, even the ABJM is actually, the ABJM is even worse. I think it's a 3, technically it's a very strict example of a 3 algebra. I think that Christian wrote something about that, but I'm not sure. But in any case, they are higher structures already. They are based on higher structures already, even if they are expressed, you know, in a way that is very normal to us, Lie algebras.
That allows you to go around this no-go theorem.
In this one very specific case, yes. Well, does it allow? Yeah. Well, it's okay as an effective low energy theory, yes. But eventually, I'm supposing we can agree that things will have to be quantized eventually. So at some point, we're going to have to. Well, in ABJM, I don't know. I don't know how you would go about it. I guess in the BLG model, there was a hope that this triple bracket that they've introduced, which ultimately, you know, is related to the other, to ABJM and to these structures, was hoped to be already a quantization of maybe a Nambu-Poisson structure of degree 3, right? But it wasn't. It can't be because, and it's not because there's something missing, because that's being based on strict Lie algebras. It doesn't have the complete structure that a quantization of a Nambu-Poisson structure, for instance, if you believe that's the thing to quantize, would have. And even other proposals. I mean, any type of seeing it as the quantization of anything failed so far, as far as I know. While I'm going to argue the last day that these N algebras at least fit, and they don't violate anything to be quantizations of Nambu-Poisson structures. So might be the way to look at it. Doesn't mean that it's still, effectively there are certainly scenarios. I mean, if you want. Well, we'll see later on when we do the two-gauge theory, but there are many examples of two-gauge theory in physics. There's the BLG structures, there is topological gravity, there's spin-form models. Spin-form models are completely based on representations of Lie algebras, or strict Lie algebras, meaning with a G and a H, Lie groups and so on. So,
as far as I understand, maybe I'm mistaken, BLG describes two and two brains, and that's equivalent.
If stacks of M2 brain, I mean, effective theory of stacks. Yeah, okay. So okay, no, sorry, what's the problem?
It's equivalent to ABJ.
Yeah.
So at the end,
yeah, that's what I'm saying. I mean, that the structures that have been proposed and have had some success, they are successful up to a point. There is a moment when you realize the quantization is the first issue, that this is still an effective theory. Then this will come from what? Like in the stringy case, I know where this effective, I know this effective theory, this thing here on p dimensions, I know where it comes from. Well, not from quantized theory, not from. Okay, let me make a parenthesis quickly. There is a model, a string theory, in string theory, there is a proposal for a completely quantized non-perturbed, quantum version of string theory, which is the reduction of super Young-Mills theory from, let's say, 10D or whatever D you want to 0 dimensions. Where the matrix model, exactly. So the action will be the trace of some commutator of these two Lie algebra valued fields squared. And this relates nicely to string theory as we know it, but written in the Schild gauge, particular gauge. I'll put the reference in the notes and you can look this up. But basically where the string theory will be written as Poisson brackets on the string world sheet. So basically, you would, since this is an honest to God string theory action, and this is the effective super Young-Mills theory, the effective theory reduced to a point. So you can imagine as if you were zooming into a point, and there is a sort of, you could say, some sort of a classical limit if you take the Lie bracket to the Poisson bracket, which reduces you to string theory. There is some sort of a sense in which you could imagine that, this is the picture, that the full quantum theory would be this, non-perturbative theory would be this model. And then if you just know how to take classical limits and so on, you would get to all the stuff you need. Now in M theory, even with, try with ABJM or try with BLG, try with something to get some sort of similar, even just conjecture. I mean, we are hoping to be quantizing something, right? I mean, we're not interested even in these like weird fuzzy properties of space if we're not quantized, if we're not quantum. Classically, we don't need any of this. We don't even, we're not bothered. But of course, certainly, many of the approaches that were done kind of trial and error and ad hoc do fit into the higher gauge theory language. And I'll show you, I wasn't planning to show exactly how to get at least the BLG structures from the 2 algebra, but we can have a quick look at it. And then if you know how to, I don't remember how to do the equivalence to ABJM, but if you do, then you can figure it out. And I can give you the reference to the paper telling you what the ABJM structure is in terms of an algebra. Okay, sorry, but it's a long discussion. Thanks.
So we can have a quick break now. bit, but I wanted to stop you because you needed to go.
Yeah.
So like artists are like even when they try to make loops into groups.
You know what? It's not. I don't think it's that important the requirement because once you the strict gauge theory definitely is because the associativity of the composition is crucial, right? But what I want to do later or next day, at the end of the next lecture, is actually go up one step to the semi-strict case, where basically the associativity of this basic composition of class is relaxed. They can be associative up to some. Sorry, that's it. Yes, you compose them into smooth class. Sorry, yes. So they don't need to necessarily. Well, they don't need to necessarily be smooth, right?
Because we learned these parts are parameterized.
Yeah.
This is the basic thing we start with. Then